Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. If you watched my video on introduction to limits, you know that I just had you guys using the graph and kind of tracing it, or just substituting an x value close and making sure that the left side agreed to the right side. However, we want to go ahead and expand that. Okay, so they might ask you to do something as find the following. And a lot of times in calculus, I use two lines to write the limit with the x approaching underneath. If you have really good handwriting or you're not trying to make this super neat, you can squeeze it all onto one. Okay, so let's say I have something written like this. What this really is telling me to do is find the limit as x approaches -4 for f of x plus 5 times the limit as x approaches -4 of g of x. And so that, all I need for that is the graph, right? So for f, we can see f is in this darker color, and I'm approaching -4. So here's -4, so my fingers coming together at 1, 2, 3. I know the point is clear up here, but we want to use this 3. Remember, a limit is not the location of the graph, it is what value you're approaching. We're not getting closer to the point, we're getting closer to the open circle as we get closer to -4. Okay, now on g, as we get closer to -4, I know there's this gap here, I don't care. As we close in on -4, my g value is closing in on -4. Okay, now we have a simple computational statement, 3 plus 5 times -4. We're going to get -17. Okay, so let's try a second one. The limit as x approaches 3, f of x, g of x. Whoops, bracket. Okay, so now we're approaching 3, and this is f of x times g of x. So let's see, f. 3 is right here. So, well, definitely is closing in on a value of 4. G of x, closing in on 0. So that product would therefore be 0. So you can use the graph to find advanced computational limits. So let's think about the limit as x approaches 5. Okay, what does this mean? Well, remember that's our function. Okay, so if I were to graph the line 8, I'd be coming in here and graphing the line at 8. So if this were 5, as we're closing in on 5, what are we closing in on? What y value? Oh yeah, it's still 8. Let that refocus. Come on. So the big idea here is that when you have a constant function, that's like setting the cruise control in your car. Your speed is always supposed to stay close to that cruise control that you set. That's why it's constant. So the limit as x approaches any constant, so any c value, and that's your number, you're just going to get out this. Okay, if there's not a variable, it's just going to stay the same thing, right? Okay, so let's see what happens when we get a little bit crazier. Okay, what about the limit as x approaches 6 of this line right here? Okay, so now we have a function. So we can think about our graph, right? So 6 would be right here-ish. What y value is that? Okay, well, we'll come back and we'll use our trick from our previous video. There's our equation. And here, we'll go to at 5.9. We're, okay, 5.99, 5.9999. We're getting closer and closer to 8 from the left. What about 6.01? 6.000001? That's also closing in on 8. I think you guys could agree that our finger is getting closer to 8. Now, some of you might be yelling at the screen going, I just did this. Anyone just substitute 6 in? Yeah, that's actually one of our rules. If you can do it. Sometimes you'll get an undefined answer and then you're going to have to fall back to your graph. Your graph is your safety net. So the limit as x approaches a number for a function is going to be equal to the substitution. Okay, so let's try that. Limit as x approaches 5 of this here. Okay, well, I'm going to go ahead and graph it just because. Okay. It graphs like a straight line. Sweet. And if I have the calculator do my substitution for me, and I substitute 5, I get out 6, which hopefully you got the same thing as well. Because the rule says we can just substitute, and we get 24/4, which is definitely 6. Okay, same equation, but new limit. We're going to approach a different x value. Okay, so substitution. 1 squared minus 1 over 1 minus 1, 0 over 0. Anytime you have 0 over 0, this is what we call an indeterminate form. We do not know whether this exists or whether it does not exist based off of this right here. However, looking at my calculator, it should be existing. Let's check. 1 obviously is blank. What about 1.01? Okay, 1.000001. It's saying we should be getting 2. It's saying that's our limit. Let's check. 0.999999. Yep, also 2. So why is the limit of this 2 and our calculator's able to get us close by using a decimal, but I can't do substitution? Well, let's think about x squared minus 1 itself. Okay, I'm going to rewrite this on my next page. It factors, correct? So this would be equivalent to the limit. And yes, you really have to write that every single time. I know you want to shorthand and just kind of get the thought process down on your paper. If you do not write the limit as x approaches 1 every single time, you have incorrect notation and points can be taken off. Now this reduces, it's a removable discontinuity. If you remember those removable discontinuities from your college algebra class, now we have the limit as x approaches 1 of x plus 1. And now I can substitute, and once I substitute, then I can stop writing the limit. 1 plus 1 is 2. So make sure you're writing the limit all the way through. Do not get messy with your shorthand and things like that. Please do not do that. Okay, a very popular limit to practice is coming up. You'll need to be able to do this algebra, okay? We'll expand on this in the future, but the limit as h approaches 0 of 3 plus h squared minus 9 over h. And right now it's an indeterminate form because if you substitute 0, we would get 3 squared minus 9 over 0, or 0 over 0. So that's indeterminate form. So we're going to actually have to algebra this out. Okay, so we are going to first go ahead and expand that quantity. So we'll have the limit as h approaches 0 of 9 plus 6h plus h squared minus 9 all over h, which would therefore become the limit as h approaches 0 of h squared plus 6h all over h, which is the limit, oops, I forgot my arrow, as h approaches 0 of h plus 6, right? And once we substitute 0, now we can find out that it equals 6. If you get lazy on your notation, do not be surprised if your professor starts taking off points. Okay, now, I've actually kind of already talked about this, but we'll just double check. Let's say you have something like the limit as x approaches 2 cosine of x minus 2 divided by x minus 2. You're not going to be able to algebra this out. So this is where that squeeze theorem comes in. Okay? We know we cannot substitute 2. So the squeeze theorem really, we're just going to kind of come in here. Look at graph, test, here's our number, right? 1.99999 and 2.000001. We're basically going to squeeze it. We're going to make sure that it matches on both sides. That is actually a rule. That's how you can compute the limit if you ever get stuck, is just squeeze it out. Does the left side match the right side? So let's check. Now, first of all, there's no degree symbol in here, so make sure that you're not in degrees. So let's make sure we come in here and we change our mode into radians. Most of the time in calculus, you're going to be in radians, not degrees. Okay? And our y equals, we want our fraction. That is my dog you hear. She's having a nice dream. And we've got x minus 2 over here. Okay, and let's pop up this graph. I must have asymptote detection turned on. I'm going to graph it faster by turning that back off. Allie, wake up. Okay, so we can see that there is a vertical asymptote at 2. And if I try to calculate, there is no. So as we've talked about, let's calculate that 2.01. See how that's a positive 99? And 1.99 is at negative. I think those are definitely very different. Those are not coming together. We can also see, boom. Okay, so this limit does not exist. Let's change it up. Let's do the limit as x approaches 2 of the sine. Will that change things? Maybe it will. Let's pop this in, and we're going to change cosine to sine. Okay, we don't have an asymptote. Can I calculate the value at 2? No, I can't. But can I do 1.9999? Looks like I'm getting out 1. What about 2.00001? Looks like I'm also getting out 1. So it looks like when our finger comes together at 2, it's getting closer and closer and closer to the y value of 1. So the ordered pair did not exist, but the limit did exist and at 1, and we got that by using the squeeze theorem. We found out that f of 1.99 was approximately the same as f of 2.01. So the limit existed. Okay? So that's always a way you can check, is to make sure that from the left side matches the right side. So if you can't substitute and you can't reduce your fraction with algebra, go ahead and use that squeeze theorem anytime you get stuck. It will be your saving grace. Also, using your calculator to graph it out, if you have access to a graphing calculator, is a great way to do a visual check. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.